Welcome to AI at Scale. AI applications in recent years have gotten increasingly sophisticated, integrating online feature stores, specialized model hosting services like ONNX and NVIDIA Triton, vector databases, and various functional transformations in the midst of it all. Tying it all together is often typically some kind of bespoke middle-tier service that calls into these various different services at different times, everybody building their own. What I want to talk about today is possibly making that more generic and more reusable for application development. I've been doing this for the past couple of years as a principal architect for AI and search at Salesforce. And before that, I did this kind of thing at LucidWorks, the Allen Institute for AI, and a couple of social media companies you may have heard of. To get a picture of how the current state of multi-stage AI inference happens today, let's do a zoom through of a schematic architecture of a fairly complex multi-stage AI app. And then we'll zoom in on an often overlooked but highly central piece, inference orchestration. So before we get into the complex world of AI, we start with a simple three-tiered web app. It has a UI tier, core business logic, and its data tier, MVC, for those of you old enough to remember their design patterns. Now, AI thrives on data. One form is that of UI events, ideally in some structured format. This is where you often get a lot of your implicit training data from. At the same time, your main DB is obviously a key piece of any AI application. So it's emitting a change stream onto some kind of document bus. And both the event stream and the CDC stream join together in your data lake, which is where we'll visualize your async compute, both in batch and stream form, lives. Now, the prototypical AI batch process, of course, is model training, training all those sexy models. And meanwhile, the possibly Lambda architecture kind of process of stream compute is also happening in AI systems, and that's typically something like hydrating all your feature stores. So note in the following, whenever you see on this presentation file cabinets, we're doing fetching from some kind of feature store table. And whenever you see Derek Zoolander and company, a model inference is happening. Okay, so that's the asynchronous world of ELT, training, and all that. The main focus of this talk is the synchronous side of complex AI applications, on-demand inference. And in particular, the AI middle tier. Client requests come in from the left and travel in a clockwise fashion is the way we're going to follow it on this diagram. There's first some pre-processing, some candidate result selection, some sorting, aggregation, and ranking of those, and then post-processing before we return. If this looks a lot like a search system, it's because I'm a search guy. I build search applications like an AI application. I build AI applications like a search application. They're kind of two sides of the same coin, and I've kind of seen it that way for the past 15 years or so. Now, pre-processing may not be just simple lowercasing of strings and resizing of input images. There are often, for example, entire personalization services. This is what I did at Twitter. We built an entire personalization service to model people's user interest. And then also, if you've got a text-based application, you may have an entire natural language understanding team that has a natural understanding service that they host various processing of text understanding. And these need to be consulted as input text comes in before you even do any candidate selection. But after all this pre-processing, in many applications from chatbots, contextual recommenders, to personalized and federated search, a retrieval step with several different search engines and vector similarity systems that are consulted. I won't dig into great detail here in this talk, but there can be a lot going on here. Any given search index in the back end may have multiple layers of matching, ranking, and re-ranking layers. Some inside the search cluster itself, as shown here, but some will show up later outside the system that is search focused. Now, all these various result candidate selection steps bring back all of their candidates into the AI middle tier for aggregation, which itself is a relatively complex process involving doing a runtime join with various feature tables keyed on the record IDs of the various search indices in a way that the features fetched are the right ones to feed into various ranking and selection models. And then finally, we can return a solid prediction or predictions to the waiting REST or gRPC call that's been hopefully only sitting around for 50 to 500 milliseconds or so. Okay, so that was a speed round through a complex AI application at inference time. Let's zoom in on another view of, say, a chatbot. And let's break down the inference into distinct categories. This is really the same thing we were just looking at, but instead of grouping these services as the document metadata service and the personalization service and the natural language service, let's isolate them into things like, are we doing straight up model inference? Are we doing a data join on a key value, similarity, or SQL store? Are we doing stateless functions as a service? Just code, no data. And then this thing that I'm calling the Inference Graph Execution Service, IGES, that's stitching it all together. These are the 4 distinct kinds of things that are happening in this chatbot, color-coded. So all this logic is still the same as what we were talking about in the other diagram, but we've kind of grouped them together into pieces that can be now orchestrated through the middle. This is the business logic of the AI application, the IGES. It's playing the same role as the AI middle tier from before, but now we're going to do what tech people do most, abstract it. The Inference Graph Execution Service is a generic service to host AI applications at scale. It's a synchronous directed acyclic graph executor. The nodes of this DAG were described before. They're joins, pure functions, model inference, and one I didn't show in the chatbot case, data sync, key value store, or stream writes. You might ask, don't we already have DAG executors? There are lots of DAG executors out there that we've been using in the AI stack for years. Airflow, Azkaban, Uzi. But these are for managing jobs and artifacts. These are lifecycle orchestration. Well, what about Spark, Storm, Samza, etc.? These are data flow orchestrators. They're primarily used for batch and streaming compute. What the IGES is all about is synchronous workflow execution. There are some examples of that already in the open source world, in addition to the industry closed source ivory towers. There's Kubeflow serving, Selden orchestrator, AWS step functions, and Ray serving. If you want to read a blog post about a typical example of this from inside the industry from more than 10 years ago, my search team at Twitter wrote a blog post about the blender, is what we called it. Now, Kubeflow serving, Ray serving, things like that are mostly what I'm talking about for IGES. But there's a slightly related but distinct type of inference computation graph as well. Deep learning frameworks like NVIDIA Triton have this notion of model ensembling that is a little different than what we're talking about here. They kind of break up an inference graph, if it's a computation graph in a neural network, into discrete chunks and let you ensemble those together in various different ways. These have fantastic performance from the benchmarking I've seen, both at a latency and throughput standpoint and memory usage standpoint. But they're not very RPC friendly for good reason. You're not trying to call out to another service in the middle of passing compute through a GPU layer. So you don't do any data fetch in model ensembling. They have great modularity as well for mixing and matching models if you fit their particular framework of being essentially a neural network, a TensorFlow graph or PyTorch graph of some kind. So these are great. I love them. They play a role in AI application development, but it's not really what I'm talking about here. The chatbot example that I'm talking about here needs this yellow piece down the middle, this synchronous DAG execution system with all these different types of graph nodes. So this is a stateless service that talks to a lot of other services. It's got generic RPC scatter-gather. At a high level, it's got pluggable remoteness. A DAG node itself is code that says I can implement tokenization or text embedding or vector similarity lookup. The node itself could be implemented locally as a client to a remote service, or it could be hosting actual logic that is hosted inside of the graph executor itself to save on RPC calls and remote latency, or it could be hosted remotely for independent scaling if you're willing to pay the remote RPC cost. The framework itself needs to have per node and per graph metrics, timeouts, and logging. These cross-cutting concerns shouldn't be left to each node type to have to implement it themselves. For good performance, we want to have this overall system be completely stateless with async primitives, kind of future-based in a netty-style way, to handle high concurrency. And an API we're going to get to in more details in a second, but it should have a strongly typed IDL that has a good schema registry of the different node types and what their inputs and outputs are. The node inputs need to be able to handle coming from multiple different kinds of places and merge together when it is passed into each node. So they're going to come directly from the client, they're going to come from upstream DAG nodes themselves, or they're going to come in as side channel input as configuration. And we'll kind of go through that in a little bit. So the protobuf interface is going to be a standard request response style format. We've got an execute request and an execute response. Requests have kind of two parts: the graph that you want to execute, and then the payload of what you want to hand to that graph. In particular, the graph is just going to be a map of IDs to the node instance configuration. The node themselves has a node type that describes what it is. Is this a data fetch from a feature store? Is this a SQL lookup? Is this a ONNX inference? Is this a whatever, function as a service? It's also got its list of all of its dependencies of what DAG node IDs does this one depend on and must execute after they're completed. And then it's got this side channel input that, again, I'll talk about in a second. But in particular, this node type is important to call out because we're saying that we're going to explicitly enumerate all the different types of nodes that are possible in the IGES. This is basically a service registry describing you can do joins and stateless transformations and inference, and you can do data syncs. The node type registry has another part. The input payload is also strongly typed for each of the node types. So basically, each node type has the form of basically being a full gRPC microservice directly. They have input parameter type, so the feature store node has the feature store input protobuf as its input, and it returns a feature store result as its output. This way, if you've got bespoke services of your own that you want to play a role in the IGES graph, just register their protobuf input and output with the plugin params registry, and it then can act as a node in the inference graph as equally as any of the others. So to recap, the request message schema has both the graph definition, some URI routing information where the DAG node will be executed, and a strongly typed payload. But in the graph itself, it has a bit of this side channel input. So the input into each DAG node comes from the client that was specified directly. That's the input payload. But you also, inside the nodes of the graph itself, have some input that looks just like the input to the DAG node. So this is a little bit weird at first, but if you want to take the example of data that might be needed for inference of a particular DAG node, say text embedding is a DAG node. From the text embedder's perspective, it doesn't differentiate whether the field that came in, the text directly from the client that came all the way, from upstream, or the input feature name, the slot on the TensorFlow graph to look up, or the output embedding feature name. From the perspective of the text embedder node, it knows it needs text input, input feature name, output feature name, embedding dimension. That's what it needs to execute. The fact that one came from the client and 3 of them came basically as config, a model already knows what they're supposed to be, is independent, is irrelevant to it. So we're going to allow our inference graph nodes to take data from both sides, the kind of config store as well as from the client, and then the dependencies as well. So we've got the IGS API, but the graph alone is going to get pretty intense. When you flesh out the graph with JSON formatting, here's an example from what we've been doing at Salesforce, kind of in schematic format. A content recommender might have a graph config that looks like this at the beginning. You've got some pre-processing, some query embedding, some candidate selection, and it keeps on going like this. This is something like what we have for question answering at Salesforce, but I've actually abbreviated it quite a bit to remove clutter. This graph config is error prone to write, and in an ideal world, this would be generated by code. You'd have a Python DSL that you specify this is the inference DAG that your application needs to execute. And when you hit compile, it kind of stores this config as a representation of what your application needs to do at inference time. This is essentially what reserve does. And if we contribute this kind of idea back to places like Kubeflow serving, that would be great as well, because the, Kubernetes world is really fond of these big YAML constructs, but not so much on the write it in code that can be more easily type checked. So at the end of the day, what I've described here is this inference graph execution service, an AI middle tier that lets you scalably build applications in kind of a more serverless way. It's a synchronous DAG executor that does generic RPC scatter gather. There are existing things in the open source world that are starting to do this in reserve and Kubeflow serving. They don't quite have all exactly the same features that what we've done at Salesforce internally have, but I'm hoping that as we evolve them forward, everyone will get the ability to build AI applications without a completely bespoke AI middle tier. I hope this was enjoyable and educative, and I'd love to collaborate with all the rest of you more in the future. Thank you.